Hello everyone, welcome to lesson 2.2 of Precalculus. We're going to be talking about the change in linear and exponential functions. So in this lesson we are doing the official connection between what we talked about with sequences and with functions to bridge that gap between linear and exponential and then officially start exponential functions in the next lesson. So let's get started. In this lesson here, we're going to be talking a lot about big ideas in the beginning, so hopefully it makes the video a little bit faster, but it's probably going to be a little bit more boring, so I apologize. So linear functions and arithmetic sequences are very similar. They have similar behavior and they have similar forms. First of which being slope-intercept form and the zeroth term explicit. They look very, very similar, and in fact their parts work in the exact same way. We have the y-intercept b, we have the initial, the zeroth term of a sub 0. They're both the initial value. Then you have an average rate of change in m, and you have an average rate of change in d. Those are exactly the same. The x is replaced with an n, but essentially they're exactly the same. They behave the same. Major difference is that a line is a continuous, smooth curve, and a sequence is a lot of dots that go in a linear fashion that follow along a line that would have continued forever. There's another form, and it doesn't get talked about as much in Algebra 1, but it is extremely useful in precalculus and especially calculus, point-slope form. So I've gone ahead and written the traditional point-slope form as it's been taught to me and will be taught to you and then students after you. Y minus y1 equals m times x minus x1. Or if we want to think about it more function notation-esque way, we can add the y1 to the other side and then just change the y to f of x and the y1 to f of x1. Perfectly fine. Follows the exact same rules. They are equivalent. They're both point-slope form. Then we have the kth term explicit. So we talked a little bit about this one where we could just pick any term. We don't have to pick the zeroth one because we're very rarely ever given the zeroth term. And it would be defined in a very similar way. We have this y1 or this f of x1, and then adding the slope or the average rate of change times x or n minus the term number or the input, the x. So follows the exact same principles, and that's what makes it really, really nice. Exponential functions and geometric sequences also have very similar behavior. In fact, their forms are also identical with each other. We have a basic exponential, which is f of x equals a times b to the power of x. And then we have this zeroth term explicit, which is g sub n is equal to g sub 0 times r to the power of n. So exact same idea where a and g sub 0 are going to be your initial values. And then b and r are your common ratios or your growth factors. We can also shift exponentials, and that's where we get this shifted exponential equation. We have the exact same setup. It's something times something to a power, but in this case, instead of the initial value, we have just a value. And then we are raising the power to x take away the input for that value. And then our kth term explicit is exactly in the same fashion. The major difference between what is a function and what is a sequence, again, is sequences are discrete. They are lists of numbers. You can use set notation to describe them. So you have the curly braces, you have lots of commas. So that is set notation, that is sequences. Functions are curves. They are smooth. For example, we use intervals like negative infinity to positive infinity. I do want to put a little side note. Not all functions are smooth curves, but the functions that we will be spending almost all of our time with, which are called the parent functions, are, and therefore the functions we deal with are smooth curves. So, la-di-da-da, let's actually do something. So, we have 3 sets of points, and each of them describe a function. We're going to determine if that function is linear, exponential, or neither. So, arithmetic sequences had addition of the same number every time, that common rate of change. Geometric sequences had the common ratios. You'd multiply by the same number every time. Well, that just means that if you're adding the same number each time, it's linear, and if you're multiplying by the same number each time, it's exponential. You do have to be careful that the x values, the inputs, are incrementing by the same amount. So we have a 2 to a 3 to a 4. Those are all going up by 1. So now we can accurately look at the y values. So we are going 1 to 4 to 16. That looks like multiplication by 4 to me. So if it's multiplication by 4, then it is exponential. Exponential. And we can say that the ratio is 4. Now if we look at this function, we go from 5 to 6 to 7. That's also going up by 1 on our inputs. So let's look at the y values. We have 3, 7, 10. 3 plus 4 is 7. 7 plus 3 is 10. We're not adding the same number here. What about multiplication? Well, if we were to multiply, we would multiply by the last number over the first number, 7/3. Is this one 7/3? No, that one is 10/7. Not the same. So it's not arithmetic, not geometric. So this one would be neither, no ratio, no common ratio. It might help if I could spell it. No COMMON ratio or rate of change. Last but not least, let's look at the last one here. We have 3 to 5 to 7. Those aren't going up by 1, but they are all going up by 2, which is perfectly fine. As long as we're incrementing by the same amount, that's all that matters. So let's list out the values. We go from -1 to 7 to 15. -1 plus 8 is 7. 7 plus 8 is 15, so we're adding 8 each time. So this one would be linear, and the rate of change is 8. Not too bad. So again, if the x values are increasing at an equal rate, and f of x is changing at a constant rate, then it's linear. If it's proportional, then it's exponential. Not too bad. So here, they're telling us that we have a linear function, and we have 2 points. So before, if we're only really given 2 points, we can't tell if it's exponential or linear. We can kind of draw an exponential or linear through any 2 points that we want. That's why they gave us the third to actually determine. Here, they're giving us 2 points, but they're telling us it's linear, which means that we have an average rate of change. So let's find that. So the rate of change, or the slope, we know how to find slope. That's y2 minus y1 over x2 minus x1. Doesn't matter which one's which. 1 minus 7 over 8 minus 3. Remember that since these are in the same point, that they have to be in the same position. And I get -6 over 5. So that is our slope. And we can write an equation in point slope form. So y minus y1 is equal to m times x minus x1 is point slope form, my favorite. Doesn't matter what point you pick. For kicks and giggles, let's pick the 3, 7. Why not? So y take away 7. Y take away 7 is equal to -6/5 times x minus 3. That is fine. That is perfectly fine if you want to leave it that way. But typically, you want to describe your equations as functions using function notation. So this is indeed a line that goes through those points, but it is not written in function notation. So you have 2 ways of going about it. We can move the 7 over and then replace the y with f of x. What that would look like would be f of x is equal to -6/5 x take away 3 plus 7. And that would work. Or we can actually simplify this down into essentially y equals mx plus b form, the slope-intercept form, and then just replace the y with the f of x at that point, which does look a little bit strange, and we don't necessarily have to do, but you can. So we can distribute and then add 7 to it, so that would be -6/5 x, -6/5 times -3, -6 times -3 is +18/5, and 7, we're going to add 7 anyway. 7, in terms of fifths, is 35/5. So we could also have f of x is equal to, and then 18 plus 35, that would be a 3. 53 over 5 would be that one. Oh, might help to give myself space for the rest of it. Got like a phantom 5 there, I guess. Negative 6/5 x plus 53/3. And that is perfectly fine. So when we have an exponential, we have to do things a little bit differently. We can't use a special slope formula like we did up here. We have to actually use an equation like we have here, but for exponentials, and then plug in everything that we know and try to solve for things that we don't. So let's start with picking a point and replacing it for the value and the shift. So we'd have y equals 5 times b to the power of x take away 2. Well, this is our x, and this is our y for another point, so let's replace them. So let's solve for that over here. We would have 12 is equal to 5 times b to the power of 4 take away 2. 4 take away 2 is 2, and I can divide by 5 on both sides, so that gives me 12/5 is equal to b to the second. How do I get rid of the power of 2? I can square root. So b is equal to the square root of 12/5. You might be like, hold up, Mr. Whaley. When you take the square root of something, you got to put the positive or negative square root, and you're 100% right. But with exponentials, your rate, your growth factor, your proportionality, if you will, is always going to be a positive number, unless we want it to flip back and forth constantly. But that's really only for sequences and not really for functions. So if we're talking about an exponential function, our b value, our growth factor, our growth rate, our proportionality, our common ratio, so many different words, is always going to be positive. So let's replace that in here. So we have, instead of y, I'm going to put the f of x now. So f of x is equal to 5 times the square root of 12/5. And you know what, let's put parentheses around that anyway, to the power of x minus 2. You can use the other point if you'd like, and you're perfectly fine. We could simplify this further. We could do something like we did with the linear function, but we just don't have the tools in our tool belt, or at least I haven't shown them to you. You might actually have the tools in your tool belt to do this, if you remember a lot from Algebra 2. But for our intents and purposes, we're just writing a function that works, and this is a function that works. So our last question we're doing together is we're given numerical representations of functions, and we're trying to determine if they're linear or they're exponential. So we have to be careful. One, our x values have to be increasing by the same amount. We have to have equal intervals in order to determine any of this. So we have to check that first. 3 to 7 is plus 4. 7 to 11 is also plus 4. So that is perfectly fine. Now we need to find the pattern. How do we go from 10 to 6 to 2? We're not dividing, we're subtracting by 4. Minus 4, minus 4. So that one is linear. So we're going to write it is linear. Now, you might be like, we're done. But we're not. Make sure that you're always reading your question. This one specifically says to justify your answer, we have to provide a reason why. So we're going to say it's linear because as the x increases by 4, f of x is increasing at a constant rate of negative 4. And you could wordsmith that a couple of different ways. You don't have to use my exact verbiage. If you're studying for a test, I would not be like, it's got to be 1 for 1 for exactly what I said. No, 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 no. As long as you're getting your point across and what you're saying makes sense, you're perfectly fine. Next up is g of x. 1 to 3 and 3 to 5 is all adding 2, so that is plus 2, plus 2. You don't have to write this every time. Sometimes it helps. It really depends on you. 2 to 6 and 6 to 18. You don't have to be rocket scientists to realize that that is not addition. That is definitely multiplication. We are timesing by 3 here. So this one is exponential. Again, we have to justify. So it's exponential because as the x increases by 2, g of x increases proportionally, so not at a constant rate, we're going to say proportionally by 3. And that is it. So a little bit of a longer lesson and a lot of talking. I'm sorry if this one got boring, but if you have any questions, please make sure you ask them in class. Otherwise, I'll see you in the next video.